He is currently based in Canada, except actually doing 3 months in CERN right now with a bunch of different things he's interested in. He's worked on everything. He's worked on quantum optics, he's worked on cryptography, he's worked on quantum algorithms, he's worked on optomechanics, he's worked on quantum optics, probably some other things I've forgotten. The most important thing is he likes being interrupted with questions throughout the talk, so please interrupt him.
Excellent. I'll interrupt you to start. Okay, thanks. So it's a real pleasure to be here. I've been in Switzerland a number of times, but it's my first time to EPFL, so, and just had the morning meeting people, and I'm very excited to get the chance to meet. As always said, I'm happy to be interrupted. I have a number of slides, but if I don't get through the slides and we have a good conversation, that's okay too. Okay, now I'll start. So I'll talk to you about superposing coherent states for fun and profit. I've been doing quantum stuff for almost 40 years, so I find that some of the value I give when I give a talk is not just on the science, but I can give you the context, kind of a bit of the history from a personal view. So when I'll explain towards the end what I'm doing. There's a theory paper, robust macroscopic Schrödinger's cat on a nucleus that I'll focus on, and the experiment that we did that was in Nature Physics last year, 2025, Schrödinger cat states of a nuclear spin-qubit silicon. So I'll build up a story about superposing coherent states, and then towards the end I'll explain how it relates to work I'm doing with the University of New South Wales experimentalists in Sydney. And then it's superposing coherent states are known as cat states. So I got a picture of a cat, and scientifically proven that looking at cats makes you feel good. So we're off to a very good start. Okay, so first I just want to give you the context for what coherent states are. So if we're going to superpose them, we should understand what they mean. Oh, is that weird?
I believe you might be.
Yeah, I think it might be a laptop setting, I would guess, because the screen piece.
And not everybody can see this.
This is intentional, it's a cat state.
Okay, I'll go down another one.
He said cats would make us feel good to look at, so we figured that's a new one. We've had other technical difficulties.
Okay, but I can't...
You should be able to, but I just...
What do I do?
Maybe you had the mirroring. Maybe the mirroring's not the one. But can everybody, could people see that or not really? No, okay, so you have to get it on those screens. Maybe if you can...
Who's good at
stuff? Teaching these rooms? I don't think, because like, it clearly is connected. It's not like, so it might be the mirrors part.
I just did the start mirroring, remember? That's all.
But maybe you don't mirror.
Well, what about you? I'm sharing. A lot of people have laptops, they could always, go into Zoom and inside.
Right.
So, okay, mirroring would be here.
Is there something besides mirroring?
Well, did that do, are they the same?
Now they're the same, but maybe try to
Well,
go
let
back.
me try this. Slideshow. Where's the view? I'll make this down here.
Oh, yeah.
I guess it's the
Okay. I'll cover this slide and then hope that when I hit down, it's... Okay, so that was the commercial break. Now, here's the story. That what's a coherent state? So first of all, this is a shot from Schrödinger's paper. So I'm using, there's the DOI service, Digital Object Identifier. They run a hash service, so when I want to cite something, if it's got a DOI, I use the hashed version. If you type that into doi.org, you get the paper back. It's a quick way of getting it. Nowadays, people are using QR codes, but you don't need it. Okay, so Schrödinger, when he introduced the Schrödinger equation 100 years ago, one of the cases that he solved is the harmonic oscillator. And so instead of doing number states, energy eigenstates, there's the Gaussian state, and the Gaussian state has 3 properties. And I'm going to tell you, I mean, it's basic physics, but I'll tell you because I'm going to come back to this again carefully later. But essentially, the Gaussian state that he introduces moves back and forth according to the harmonic oscillator motion. It's a minimum uncertainty state, so the spread in position, or the Fourier transform giving the spread in momentum, multiply to give a minimum uncertainty state by the Heisenberg uncertainty relation, and it's non-dispersive. So the wave packet width doesn't change over time. So these are three important properties for coherent states. As I get more abstract, we'll have to sacrifice at least one of the three, but this is the case. So that's really the first coherent state. So this is the 100th anniversary of coherent states in my view. At the same time, almost the same time, there's Schrödinger's original work. And so this is a picture of Schrödinger's famous paradox, representing Schrödinger's famous paradox of a cat in a box. And so in the way Schrödinger formulated it, in the box there's a cat, there's a poison gas, there's a detector of a nuclear decay. And so a nuclear decay causes a poison gas to release that kills the cat. But since we don't know, since the nuclear decay is in a superposition, so if it's an alpha particle decay, it's in a superposition of being inside and outside, and that entangles with the poison gas, that entangles with the cat. So Schrödinger's original paper was an entanglement paradox between the nuclear decay and the cat, but over time the language has changed. So the language nowadays about a cat state is not the entanglement between the nuclear decay and the cat. We just say if a cat in a superposition of being alive and dead is a Schrödinger cat state. Okay, so that's what we say. Not what Schrödinger meant, but I'm just going with the language of today. Okay, then in 1963, Roy Glauber's paper came out, and I'll tell you a little bit, but Glauber here this is the paper that got him a Nobel Prize in theoretical quantum optics, and he refers to a superposition of energy eigenstates, and the coefficient is the square root of the Poisson distribution, which represents vacuum noise, and he says we call those coherent states. So Glauber was the originator of the term coherent state, but he knew he was referencing Schrödinger's work, and it's essentially recognizing that the electromagnetic field is just a collection of modes, and each mode behaves like a harmonic oscillator if you work in a linear optical regime. So that's the case. And then actually I was in Japan a couple weeks ago talking to Yasunobu Nakamura about this. He was writing an article for a Japanese magazine. So he was interested in the history of the use of the word coherent in quantum, and then we did some digging, and so this is the original use. So the whole idea of using coherence came up here. So I'll just tell you what was going on. So back in the 1950s, there was a push to try to develop a coherent version of the maser. An optical version of the maser. Can we get microwave masers, microwave, to work in the optical domain? And the answer was no, until Shavalov and Townes patented the idea of a cavity in 1957. And so then in 1960, in the second half of 1960, 6 different lasers were invented. So the lasers were invented in 1960, but the theory was bad. And the debate, which was largely between Glauber and Mandel, was if you shine a laser beam through a beam splitter, will the photons coming out be independent of each other, or will they anti-correlate? And I've talked to both of them. They're both passed away now, but so Glauber told me that he was working this out, and he was trying to get his work into an optics journal, and they wouldn't accept it because optics people were convinced of the other way. The idea that there's the square root of Poissonian here kind of reflects that there's no correlation in the splitting of a laser beam, and so he managed to he sent to Physical Review letters because it was easier to get it in a physics journal than an optics journal. And this is where he introduced the coherent state, and it addressed that problem and many other things. So it can look trivial now, but it was a very important paper at the time and deserving of a Nobel Prize. Okay, now we'll see if the next slide works. Yes, okay, problem solved. All right, now, what am I doing here? I'm going to skip that. That's just more background on the topic. These are just people who generalize the idea, which I'll skip for the moment. And now I'll go to the next important event. So I'm going to now go on to the idea, instead of a coherent state, superposing 2 coherent states. So the coherent state is recognized as a quantum representation of something that is almost classical, right? So the reason that the cat being alive and dead relates to superposing coherent states, just like the coherent state follows the classical motion of an oscillator and is a minimum uncertainty state, the idea is that somehow coherent states are representing the classical dynamics. I'll be more specific in a moment. But the first idea of coming up with a superposition of two coherent states came up in 1974. I'm going to come back to the year 1974 soon. This was a paper out of the Lebedev Institute in Moscow, Dodonov, Malkin, and Manko. And so they introduced, in a mathematical physics context, a sum of displacement operators acting on the vacuum give you coherent states. And they got mathematical terms like U11, UN1, and so on. And most physicists don't like to look at mathematical physics. So even though it was the first paper on superposing two coherent states, most physicists either didn't read it or read it and forgot, so the paper was forgotten. But historically, that's when it first came up. Then later, Jared Milburn, so I was a postdoc, I was his first postdoc, but when he was a postdoc at Imperial College London, he was interested in the following problem. He said, let's consider a nonlinear dynamics. So he considered an oscillator with a nonlinear dynamic, and his interest was specifically in how to represent the dynamics. And essentially, it's writing Hamiltonian evolution, and then there's something known as the Q function or Ussini function. The paper concentrates on that. It's very nice work. And along the way, this is from figure 8A and B. So in figure B, using the Q function, so it's some representation in phase space, at some time of evolution, he shows that he gets a superposition of two coherent states. He doesn't discuss it in the paper, it appears, and he also showed before it gets there, half the time to get there, it's a superposition of four coherent states. And I'll talk more about this. He doesn't discuss the states, he's more interested in representing the dynamics. Later, this is off the web, I've got a bit.ly reference to it. This is the phase space, this is a Wigner function phase space representation, and you can see a superposition of two coherent states and interference fringes that if you do an experiment and measure position of momentum, in optics it's homodide detection, then these interference fringes will come up to show you the essence of that superposition. It's kind of an operational way of trying to look for what Schrödinger was talking about. And then Yerke and Stoller, soon after, they talked to Milburn, I remember this, and they mentioned him later, and they wrote an article in Physical Review Letters, and their whole article is about figure 8b. So I'm going to show you. Figure 8b led to a whole PhysRev letter article about it, and I'll show you that figure 8a became a Nature paper. So to me, it's an example, like I really like the idea that you get two subfigures and one generates PhysRev letter and the other generates a Nature paper. So there was a lot built in that. And I was lucky to be a postdoc soon after with Milburn, so I got to understand some of the nuance. Okay, now what did happen later is, so I'm just going to go into experimental right now. And so they're making these things became important. And then there were two groups. You can see the dates. This is Science from 1996, PhysRev Letters from 1996. And so in 1996, the two papers came out, one in Science, one in PhysRev Letters, demonstrating the superposition of two coherent states. So one is from the group of Wineland, another from Arosh, and if you know, a few years ago, the Nobel Prize in Physics was shared between two, not three, but that time two. So those two papers were key to a Nobel Prize, getting the Schrödinger cat state. Here you can see, I like the way they do their cat. It's a happy face and a sad face. So the cat's in a superposition of being happy and sad. It feels less violent to me. And this is actually, the entanglement with the up and down is very true to what Schrödinger was talking about, the entanglement of the cat with the nucleus. But what they do is they then transform the spin state, this is in an ion trap, and then they wind up with a superposition. So once they get there, then they're able to measure the spin in some basis and create that superposition of coherent states. Here in Arosh's case, instead of ion traps, it was cold atoms and cesium. So not ultra cold, but just cold. The cesium atoms go through, they do microwave control, brilliant experiments, not so much done anymore because the stuff that Arosh did is being replicated easily in superconducting labs. So the superconducting qubit story has greatly simplified the kinds of things that were actually really heroic to do. So in both cases, they get a superposition of coherent states. Optically, and this is from France, the group of Philippe Granger, they tried to do it optically. They made what they call Schrödinger kitten states. This is essentially a squeezed vacuum with a photon subtraction. To me, it's like we say sometimes, if it walks like a duck and it quacks like a duck and it looks like a duck, it's a duck. So it's kind of like that here. They call it a kitten because the two Gaussians have significant overlap. So because they have significant overlap, they called it a kitten. And then they show that they get some superposition of coherent states with overlap between the Gaussians. So they're not macroscopically distinguishable. And then meanwhile, at the same time, well, almost the same time, that was 2006. 2008, the group of Serge Laroche was getting better and better. And then you can see here, it's kind of kitten-like, but they're able to get good separation to get the cat state. So it's not two circles, but it's two bananas in superposition. So things were moving along to get these to work. Now this was the Nature paper that was figure 8a in Milbert's case. So Zurek calls this a compass state. So here you've got 4 coherent states in phase space. Think of it like north, south, east, and west. That's why it's called a compass state. And you can see between 2 coherent states interference fringes. And so the point of the interference is you can see the cat if you look at it in the right basis. But Zurek is saying if you make a superposition of 4, the pattern means that you will see a superposition no matter which basis you choose. So that was why it was relevant to being a Nature paper. And then he talks here about sub-Planck scale. So by the way, the Planck scale is not the Planck scale in cosmology, but rather it's what he calls Planck scale is just the vacuum noise size. So the area of that circle. And then he points out that you get this sub-vacuum noise level in any basis. And his work concerns the early universe. So he's kind of building that up as a story related to whether quantum effects in the early universe are observable. Okay, I'll go on to, then a revolution started happening where it wasn't just heroic efforts to demonstrate some cat state, but when the word came out, this is Deveray and Sholkoff. You guys might know Deveray won a Nobel Prize last year for macroscopic quantum tunneling, superconducting systems, along with Clark and Martinez. And so this paper that came out in Science in 2013, so 13 years ago, is essentially following Laroche's ideas, but being able to perform them inside of superconducting systems. And here, without going into the details, you can see that there's a superposition of 3 coherent states with the interference fringes. These are all experimental results, not theory, and so on. This is the compass state of Zurek, etc. So in 2013, through that group's efforts at Yale University, we entered an era where we could just write down on a piece of paper some superposition of coherent states we want, and then they can make them. So for me, I think, and I'll mention my own work, historic work, in a moment, but the idea that these things can be done flew in the face of we used to just, in the old days, talk about it. It was just science fiction stuff. People would laugh, why are you wasting your time thinking about it? And I'm thinking, yeah, why am I wasting my time? And I never dreamt that I would see in my lifetime these kinds of effects. Nowadays, when I go visit groups doing superconducting, they say, what are you what's so interesting? So if you're used to these happening, you don't see it. But if you spend part of your life trying to figure out how to make it work, it's amazing. And then over on the second side, there's a paper called The Schrödinger Cat Living in 2 Boxes. And so that was a science paper, same group. Where's the date? I don't see the date. There it is. Yeah, 2016. So almost 3 years later, and they have 2 microwave cavities. And so what they call a Schrödinger cat living in 2 boxes. You can see here, they say entangled coherent states. Reference 15 was to my own work introducing it. So, and I'll mention a bit about what I did, but it was, instead of like a harmonic oscillator, going like this, you could say I have 2 harmonic oscillators, and then they could be entangled. They could be going like this in one phase, and a superposition with 180 degrees out of phase. So it's, like, if you think of these out of phase, the both could be in phase and then both in antiphase. And so that's essentially what they did there. So, and then when I introduced the term entangled coherent states, it was trying to get back to Schrödinger's idea, but instead of the cat being entangled with the nucleus, it's like a cat entangled with a cat. So then that was demonstrated in that paper. And so after these entangled coherent states, well, as people were working toward it, there was Hirota. So Hirota-san, he's a retired professor at Tamagawa University in Japan, and he asked me to give, they had a workshop in entangled coherent states, and then back in, they asked me to write an article on, just open the workshop and write an article about entangled coherent states. Now in the Bible, there's something that says there's nothing new under the sun, so I spent some time thinking, okay, probably I could date it back. And I was able to date back this idea of entangled coherent states, so a superposition of pairs of cats. And I took it back to 1967, which is interesting, and I'll say more, because I told you the first superposition was 1974. But now I'm going to tell you that the first superposition of coherent states is 1974. The first superposition of a pair of coherent states was 1967. How can that be? How can the harder part be done before the easier part? And I mentioned in the abstract about the superselection principle. And so if anybody here knows quantum resource theory, it's not in the papers anymore, even in the reviews, but I can argue that quantum resource theory goes back to superselection, which I'll explain in a moment, and then entangled coherent states are relevant to that. And I'll show you the work. So this is the work in 1967. Yakir Aharonov and Leonard Susskind. So Susskind is now, he's a Stanford University professor now. This goes back to the 1967. And so the argument was the following. And actually, so these days I'm based at CERN for a few months. There's a lot of particle physicists, so I'm testing what I say. But essentially in particle physics, you go to somebody and you say, could you have a particle that's in a superposition of two charges? Or some other quantum number, angular momentum or the rest. And they'll typically, even today, say, no, you can't. And they give you a reason. But when they say you can't have it, there's nothing in the principles of quantum mechanics that says you can't have a superposition of anything. And so this is what Aharonov and Susskind were dealing with, is they talked about charge superselection rule. The notion of selection rules you get in atomic physics, transitions between different levels. The notion of superselection is you say certain transitions are forbidden. So if you think of a matrix describing evolution, and you forbid certain off-diagonal elements from being anything but zero, you're superselecting. And so they say, like according to Witt, Whiteman, and Wigner, which is the original rigorous theory of it, some selection rules can be elevated to the status of superselection rules, so it's, I think, 1940s. A superselection rule asserts the impossibility of preparing a coherent superposition of two eigenstates with different eigenvalues. And quantum resource theory, which came out of it but then forgot its origins, is essentially dealing with the problem of saying, how do I check if something is a resource and quantify it? So violating a superselection rule is essentially a quantum resource theory problem. And then in doing so, in their paper, they introduce this quantity here. So they're saying, if you think of a particle with a charge, imagine the charge is described by a Gaussian. So you don't say the electron has this charge, but you make a Gaussian wave packet around the charge. The charge is in some sense complementary to the current. And so you can have a charge current complementary to it. And then they say, but you need to have a reference. So they're saying it makes sense to talk about a superposition of charge if you have a reference to measure it against. So this integral with the delta function is essentially coherent state times coherent state plus, because the integral becomes a sum, coherent state by another coherent state. So this is the first appearance mathematically of coherent states as pairs. This is, I won't go into it, but this concept, the origin, is actually relevant in considering applications of the idea. Okay, and now, so that was the fun. Remember, it's for fun and profit, my talk. So fun is over. Yes?
Yeah, so that was actually going to be my question. In that,
Are we-
looking at it from now, when I think of cat states, I think about them for error correction, or
Correct.
I think about them in terms of finding understanding the limits of superpositions, whether you can have macroscopic quantum effects. I think about them in trying to control them, in controlled sensing, quantum rate, like there's applications in mind. But all the stuff you've done so far, where you've got Weinmann's experiment, blah, 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 what were they putting as their sales pitch when like asking for grant money?
It was essentially a foundational quantum physics question, and it's related to what you said. One of the points most of what you said was application, and then one of them was
quantumness, like
yeah,
the limits of whether you could have that macroscopic superpositions, that kind of stuff.
correct. Yeah. So the question is there some limit? And so somebody I talked to a lot about this, Tony Leggett, another Nobel Prize winner. He's got there's the Leggett-Garg inequality and Leggett inequality. It's the question of can you, is quantum mechanics going to break on some scale? It is the issue. And so the story back in those days is this becomes a pathway to be able to explore whether quantum mechanics breaks down in some way, and then is there a sensitivity, like Zurek stuff with the early universe, is there something that should manifest as a quantum effect or not? So that was the story. And then this is the point where we break into what you said. This now becomes the application.
Then follow-up question. With that story, I get that with ions when it's like motional modes, and it's really like you've got these coherent states spatially separated. I guess it's also like that in an optical context. Is it the same in a superconducting? Are they motional modes spatially separated? I don't know how to visualize
yeah.
that.
So it's harmonic oscillators is what you want. So you're right. With the ions, the ions are trapped in some sort of virtual crystal, and then there's motion. So you can rock your ions. And in that case, it could be a single ion that rocks back and forth. So it's a harmonic oscillator in a motional sense. And then if you go to the optical case...
And so I can literally think of it as like two spatially separated coherent states in a superposition.
Yep.
So it's like there's two different places.
The math is the same.
Yeah.
But each manifestation can come out different.
Yeah, so what's the manifestation in the superconducting sense? I can't visualize it.
So in the superconducting case, there you see the cavity mode.
Yeah.
So that's a microwave cavity. So it supports one microwave field mode inside the cavity. And so if you picture it, if you think of a standing wave, fundamental mode, it's a superposition of going left and right. But if you, if you can make the traveling wave picture, so there's the rocking back and forth, and you entangle the two, that would be the entangled coherent state. And then in the case of, it's essentially the way they do it is it's a microwave field inside a cavity.
Okay.
And then you just need to make it in a superposition of two directions oscillation. You lose it in a standing wave. Like if you think of a standing wave fundamental mode, then you have it's a superposition of moving left and right. But I think if you go to higher orders, if you went to a higher order, okay, maybe this is the problem. Yeah, so if you go to a higher order and you have like a superposition of left and right, you can put a plus sign or a minus sign in front. So there's a phase relationship between the two. So this is what you're capturing in the physics of cats and superpositions.
It's harder to get excited about than the ion case.
Well, this is, because I lived for a long time before they did it, and I never thought it would happen, I got excited. But you're post-selecting. Now that it's done,
It's also just less visual. Like the ion case, I can re-visualize. This one I find harder to
yeah, you want something to move.
Yeah.
Right.
But it's fine. I'm interrupting you.
No, but I want to interrupt. You're the only one interrupting.
I mean, you're a physicist. Haven't you done experiments on LC oscillators?
What?
Haven't you done small experiments on LC oscillators?
No.
No?
No.
It's kind of fun.
I did it.
I did some odds with that one.
Yeah, good to see that couple.
Okay, so review the chair's super selection. Okay, so this is where, at this point, so let me just give you the context. So this is 1997. First author, Ai Chuang, if you know the book by Nielsen and Chuang. So this was part of his PhD work at Stanford University in the group of Yoshihisa Yamamoto, and then Debbie Loom, she's a professor in Waterloo in the math faculty. So the idea was in Ike Chuang's, if you read the book they wrote, chapter 7 is largely based on Ike's PhD work. And so they're trying to go through and figure out how do we make a photonic quantum computer. And so this is an early attempt at quantum error correction stuff. And just remember the context. Shor's work, error correction and algorithm, came out in 1994. 1995, there were a slew of papers that were published, Sirac and Solder, DiVincenzo, and so on. And during that era, everybody's trying their own attempt to figure out how to do things, to correct errors, and all that. So they went through and they developed a theory for a very restricted form of error. Soon after, in the optical case, there was the work, so this is Milburn again, that I've mentioned, and Cochrane, and there was Bill Monroe. And so they wrote a paper called Macroscopically Distinct Quantum Superposition States as a bosonic code for amplitude damping. So they're essentially saying here, why don't we use a cat state? If it's a plus or minus between in the superposition, let's make that the ket 0 and the ket 1. So the quantum logical 0, quantum logical 1, and they write in the abstract Schrödinger cat states. So the cat becomes the encoding. I was in Sydney at the time. I called them up and I said that we did all this in the context of the ion trap, but like you asked, it didn't matter. Physical system, math is the same. And so then I said, you've got 1 qubit, but you need 2. You need 1 and 2 qubits. And I pointed out these entangled coherent states would give a pair of qubits. So this story, it kind of completed the story where we said, okay, you have a cat, that can be 0 or 1, but if you have 2 cats, then you can make the equivalent of Bell states, cat 0, 0 plus cat 1, 1, and so on. So that was the idea. And then very soon after, now a very famous paper came out, and this paper is at the heart of some of the quantum computing company efforts. So this paper came out a few months later by Gottesman, Kiddeff, and Preston. And so this paper is very interesting. So the paper actually was called Encoding a QDIT in an Oscillator, but the American Physical Society didn't allow the word QDIT to be used, so they changed the title. And essentially they're doing the following, and let me explain a bit. So in talking about a cat, so what we were doing a year before was we're saying, if you make a superposition of 2 Gaussians, and there's a plus or minus, that's your 0 or 1. But they're saying, well, why don't we make a superposition of infinitely many Gaussians and squeeze them so the width of every Gaussian goes to 0. Now everybody who's done an undergraduate degree in physics or math and learned about 2 limits knows that the limit of infinitely many teeth in a cone and the limit that the teeth go to 0 width don't commute. So these guys, all of them very smart, committed a sin mathematically. They said, we're going to treat the system, we're going to do bad math to get good results. And I'm going to explain a little bit, but I will point out that the math in this is similar to the mathematics of a frequency comb, which is being used for metrology. So frequency combs are very important. So the idea is they said, let's have a superposition of infinitely many coherent states and squeeze them. And then they said, that's the logical 0. The logical 1 is the same comb halfway between. The tooth is halfway between. When they wrote their paper, they point out you could have, instead of a qubit, a qubit, you put the tooth 1/3 of the way and another one 2/3 of the way. And then, if you want to do a Hadamard transformation, optically it's a delay line, you do a Fourier transform. So instead of the width being proportional to the amplitude of the coherent state, the cat, it's inverse. But then in figure 2, they then say, we did bad math, this is how you really need to think about it. And so there's a Gaussian envelope around periodically spaced Gaussian teeth, and then when you do a Fourier transform, you swap the 2, right? So the width of the envelope swaps with the width of the teeth. That's part of the reason for that invert. So they wrote a whole paper about how to do quantum information processing with light, making use of a generalized version of cats into these combs. And so they study all that. They get some very beautiful results out of it. I don't have time to tell you all the stuff, but they set up a whole theory. But this is why this is the profit part, is if you look at a number of companies in Canada, we've got Nordic Antique and various others, there's Xanadu also in Canada and other countries. The idea of going towards this kind of encoding for quantum computing has become very popular. So who would have thought that the idea of developing Schrödinger cat states would be one of today's promising approaches to doing quantum computing? And then more people have done stuff since. I put this one up, Jonathan Holmes' group, coding a qubit in a trapped ion mechanical oscillator. I won't go into it, but there's a whole set of works that go on that carry further. Okay, now I'm going to try to connect with my own work. Check the time. Yep, sorry, more or less on time. Okay, so now what I'm going to tell you is, remember what I told you about a coherent state? 3 properties. Follows classical motion, minimum uncertainty state, non-dispersive. Now in atomic physics, when you learn it and you say, what is the level of the electron, we'll learn about NLM, right? Principal quantum number, angular momentum number, and so on. That's like the Fock number states. What is the coherent state analog? And so, if you teach a child about atomic physics, you say the electron orbits the nucleus. And then quickly at university you say, no, that's not the right idea. But it can be the right idea. As long as you make a coherent state, you can construct a representation of the electron, and you can see these effects in highly excited Rydberg atoms with an electron going around. So the idea of introducing a coherent state is to try to make some kind of wave packet. Can't be Gaussian, because Gaussian, the tail goes on forever. Turns out it's a binomial. Your coefficients in your coherent state are binomial, but you can construct a representation and see in that representation the electron orbiting, but it does disperse. That envelope will change over time. So you have, for a short time, it looks like an orbital model. The paper came out in 1970. Arecki, Courtens, Gilmore, Clowder were the authors. And then soon after, Perelomov in Moscow, he thought, well, okay, how can I abstract that? So essentially you just say, give me a Hamiltonian description. So it can be hydrogen atom with a Coulomb potential. It can be some other model. It could be how you squeeze light, parametric down conversion. Give me a description. I look at the symmetry, and then he said, as long as I have a Hamiltonian and I understand the symmetries of the Hamiltonian, I can define a coherent state. And so these are now known as Perelomov coherent states because there are other versions. And so the idea is, instead of doing, if you think of a spin system as an example, instead of having spin states, you make a superposition of those. And then you represent it on the block sphere. So if you're used to doing, writing spin dynamics for, the block sphere for spin half, and you can extend it higher, this blob can represent the coherent state. Instead of being a Gaussian, it's got a binomial property to it, and it's just a superposition of those. So you say, start with a spin up state, then your Glauber displacement becomes a rotation. You have a blob on the top, you rotate the blob. So that's a coherent state for a spin system, but you could do it abstractly for any mathematical system. When I mentioned the 1974 work by Dodanoff et al., and it was mathematical, they were essentially building to accommodate that, but most physicists are allergic to the abstract math, so it didn't survive. But Perelomov is bringing that back in, and it's no surprise that the Dodanoff et al. Was Manko's group in Russia. This is Perelomov's group in Russia, and the Russians had a tradition of strong mathematical physics training. So it's not surprising that some of these ideas were emerging in Russia at the time. Okay, and then this was my own connection. I mentioned I was a postdoc with Jared Milburn, who did the nonlinear oscillator, and I kind of like math, so I thought, okay, can I abstract what he did in the Perelomov context? So I suggested over here, this is the blob, there's the nonlinear evolution, and a superposition of 2 coherent states. But instead of being on the phase-space plane, it's on the block sphere. In those days, this is 1980s, it's hard to draw things on computers, so I did a stereographic projection. Okay, now this idea is relevant, this idea is relevant to metrology. So you asked about the quantum sensing. And so this paper that came out, you can see Wineland's name again, the Nobel laureate with Haroche, optimal frequency measurements with maximally correlated states. So this paper underpins almost all work going on about quantum metrology advantage. And I was a referee of the paper. So at the time I got as a referee, and I really thought a lot about it. So it was very important for me to learn that paper. And essentially they're saying, can we make a better clock? Now if you think about the way clocks work, clocks have to have a frequency standard. And the frequency standard, you can think of a set of ions in the trap, and then the way that you lock, kind of have a beat pattern, you kind of lock your frequency to the atoms. And the way that you do it is you just drive the atoms, a Rabi oscillation of the atoms, look for a beat pattern to correct things. But they said, what if we took our atoms, or ions, and we had them all in a superposition of ground state with all in excited state? And that's what's being written here. So it's written in a spin state version, but n atoms, so then you have a spin state where they're all up and all down. In the Bloch sphere language, so basically in their theory, if you say every ion experiences the same physics, you get a permutational symmetry of your physics. If you've done mathematical physics and you know Scherweil duality, you use that trick. If you don't know it, just think of it as something like if you have 2 qubits, you can think of a triplet and a singlet. That's the easiest example of Scherweil duality. When you recognize that, then you can think of it this way. So this is how I was interpreting and responding as a referee. And so the idea of that quantum metrology paper was the cat state. This is what I wrote about in 1989, but not thinking about an application. But if I think in my way, their idea of getting better quantum metrology is essentially making a spin cat. And the idea of the spin cat, it doesn't show up in this picture, but you have interference fringes along the equator, and then actions of that. The interference fringes have a scale on the size of the dimension of Hilbert space. So essentially you're getting a linear scaling of precision with, when you're locking your frequency, the precision scales linearly with the number of ions, but if you do it the standard way, you only get precision scaling with square root. So the heart of the quantum metrology advantage comes down to cat states, not in textbooks. You got it straight from me, but that's one way to look at it. Okay, now I'll finish with the stuff I've been doing with the University of New South Wales people. So this goes way back, and then as we've seen, cat states and entangled coherent states are done. So of course I would like to see these done for a spin system. You know, can we make a spin cat? Now, there is work I didn't put up here, but in atomic systems, there are ways to create ensembles of atoms in cat-like stuff. But for me, I really want to see this nucleus in some superposition. So here's what we do. Now, I'm a theorist, so I can't take credit for any experiment. It's Andrea Morello's work. And so the idea is that he has a silicon substrate, and then he plants into it a single antimony nucleus. Antimony is Sb in the periodic table. He picks isotope 123. Isotope 123, 123, has a nucleus that spins 7 halves. That means it's got 8 levels. So it's, in my language, it would be a qubit. It's a 8-level system. And then our goal is to be able to create a cat state. So that high spin nucleus should be in a superposition of fast spinning clockwise with fast spinning counterclockwise along any axis. That's the goal. And of course we did it, so it has a happy ending. And then over here with the nucleus, there are a few things going on. One is, and I'll show you, just go down so I can point it out. Yeah, okay. So I'll explain it a bit here. So here's the antimony nucleus. It's got 5 outermost electrons, 4 attached to neighboring silicon, and there's a 5th one that's kind of just hydrogenic. It's kind of a free-like electron. And then what we do is it's implanted. Then we use the coupling between that electron and the nucleus through hyperfine control. We're able to prepare the initial state of the nucleus. Then what we do is we rip off that outermost electron. So it's essentially ionized. And actually, I'll just tell you, in the periodic table, bismuth has a spin 9/2 nucleus. But you know, if you have a Band-Aid, and do you rip it off or do you take it off slowly? And in this case, we have to rip it off. So we've got to pull the electron off without disturbing the nucleus. So with the spin 7/2 antimony 123, we can do it. With bismuth, there's a disturbance to the nucleus. So we get very lucky with that particular nucleus. Rip it off. Then what we do is we control it with microwave fields. You can see a B0 and a B1, a DC and an AC magnetic field. If you've learned nuclear magnetic resonance, it's that technique. So we're using NMR techniques with microwave fields to move, basically to control the spin of the nucleus. And over here, what we do is we apply electrostatic interaction. So the silicons cause a torsion on the nucleus. So you have this nucleus, and then you kind of force it in some way. That gives the nonlinearity that we need. That causes non-uniform spacing, nonlinear spacing of the spin. And then with the microwave field and a superposition of 7 frequencies, we're able to control that and make cat states. So we just hit it with multi-tone microwave fields to create the cat states. These are the experimental results. You can see superpositions. We're able to go into submanifolds. So it spins 7 halves, but we can deal with, we can skip levels and deal with spin 5 halves, spin 3 halves. So we study scaling. This is like the sphere. This is a representation which you can also do in like maps of the world. You pull the back end and fold it out. But essentially we're studying, and we get very clean signatures of that. So we basically managed to get cat states for high spin nuclei.
Sorry, I'm just a bit, I think I just skipped out for a second.
Welcome back.
So what's the analog of Petrov measurement on this, in this kind of setup?
So the measurement that we do, we use the hyperfine interaction to prepare the nuclear state, strip away the electron, and then I'll go back one. We reattach the electron, do standard electron paramagnetic resonance techniques, and I didn't say it.
Yeah.
So when we reattach the electron, then the SET is a single electron transistor, and it's set up so it's spin selective. So we're essentially doing population measurements by reattaching the electron, coupling it to the nucleus, measuring the spin, and then from that we infer what the state of the nucleus is. So it's prepare the neutral, ionize it for microwave driving control of the nucleus, reattach the electron for readout.
So in the analogy to the optical coherent states that you're preparing here, your main control is over here. It's a Fock letter or the discrete.
Yeah, so in the optical case, we talk about homodyne detection of that. If you go back through like Roche's experiments and even what they do in superconducting systems, they'll do these parity measurements. I don't know your background, but you know what I mean?
Yes.
Yeah, okay. So in the end, the spin that comes off is like a parity measurement.
Yeah.
So we're going back more to the strategy of use parity measurements to build up through your data something that you can construct the state.
In these kind of setups, do you have any natural version of displacement operators?
Yeah, the rotation.
Yeah. And
So-
you have good control over them, just by the electromagnetic field.
Yeah, so the idea is, it's like the analog of displacement is rotation, so we can rotate a blob. And then how we rotate the blob in a high spin system is this. By having the torsion on the nucleus, it creates a nonlinearity of the spin, which causes unequal spacing between energy levels. And that means we can drive rotations between any pair with a different tone of the field. And so by doing this effect, we can get a rotation.
So similar to Jonathan Holmes' experiment, can you engineer something like a controlled displacement in this setup?
Now I know what you're getting at. Okay. So you want entangling operations, right? Yeah, okay. So in the work we're doing, the antimony is isolated, so there's no other one to attach to. On the other hand, and this is Andrea's PhD work, well-known stuff on 2 phosphoruses in silicon. So if you take the phosphorus atoms and deposit, they're spin half. And then there have been some heroic experiments where they're showing entanglement, which allow you the gates you need to do a controlled spin flip. So it's a controlled Z or a controlled X or something like that. So you're able to construct that. The question would be, like, the way that those experiments are done, you have 2 phosphoruses, and then they share an electron. And the shared electron is used to be able to entangle the 2 spins. So if we could, there's all things that we think about, we would do something analog, and instead of, we'd have 2 antimony, and then we would have a shared electron, and then use that to try to make it work. That's loosely the concept. But that's all really important possibilities for future work. So you're asking a very important question. Right? And then it's not like we say the controlled displacement, it's a controlled rotation.
Yeah.
but your control, it's basically a qubit. You know what I mean by qubit? So it's a qubit and a qubit. And then the qubit level here controls the rotation of that one.
Yeah, that's what I'm wondering about. Whether you know Victor Albert's molecular
Yeah.
codes, like GKP-like things, and
Yes.
engineering these kind of systems. Like, can you envision those as feasible in
Well,
this kind of setup?
So I'm kind of a hardcore theorist like math. So of course I can write down mathematically that operation.
But sure. Yeah.
But can we make it in real life? I don't know. And can we scale up to 3? I don't know. Okay, so since you're asking, I'll just tell you a subtlety here. Okay, I don't know who knows. I don't know the backgrounds you guys have, but there's the work by Bruce Kane, 1998 Nature, first proposing using NMR techniques in silicon. Anybody know this? Maybe not. Okay, so in Bruce Kane's version, there's 2 phosphorus, each one a qubit, spin half nucleus, each one with an electron, and then the mutual control is a Coulombic interaction between the two, Coulombic and spin-spin, so magnetic and electrical interaction between the 2 electrons. But the way the experiments were done, eventually, is one shared electron instead of 2 separate electrons. And so for me, I struggle with that, because the Bruce Kane idea has a scalability to it, but it never worked. And people are pessimistic about getting it to work. The same problem comes into here. So when you're asking the questions, the challenge of whether you have 2 electrons interacting or 1 electron shared is, to me, very important in looking at what's feasible. So I worry about those things. I don't have a good answer, but I'm just telling you one of the foremost feasibility questions I have.
So say you just decide you don't care about scaling it and you're just happy having this one, does it still have metrology, sensing, other applications, or is it just cool?
So these are written in, am I being recorded?
Yeah, I think you are.
Am I? Okay. All right, so the answer.
So, I was wondering, I do think it's fun, but what do you put in your mind?
The problem, well, you don't, because this is the energy levels here require you to operate at liquid helium-3 temperatures. So how do you put something in a dilution refrigerator and carry it around? Papers are written, that's why I'm checking how much is being recorded, but if people writing papers will kind of say, we showed this under these conditions, and under those conditions it's relevant. But I don't buy those arguments, but I don't want to say publicly too much about it. But if you do something in dilution refrigerator, it's hard to know what your metrological problem is.
Magnetic field? Could it be? No, you're right. You can't move it around. I completely agree. Yeah.
Yeah, they do a lot to try to get rid of magnetic fields. And then even reading stuff, like, you don't have access to a lot of information. Huge set of problems with that. But,
So your line is to try and scale it. It's not sensing, it's not metrology, it's to try and scale this and eventually do information processing? Or it's just cool enough, so I'm saying?
yeah, I don't care if anything's useful.
Sure.
I'm okay to live in a cave.
Okay.
So for me, it's really a question of this. It goes back to the earlier question, the foundational stuff. So I'm okay. I think quantum mechanics is right. I'm not trying to explore that, but on a technical level, I find it really interesting to push how much we can get that really needs quantum mechanics to describe. But I don't look at it personally as philosophical or foundational. For me, it's kind of how far can we push our tech to see wonderful quantum things. So that's my driver. I think I can laugh. That's probably. Yeah, this is just junk. Oh, this is explaining the details, more detail. Oh yeah, these are just details where, I'll just mention this briefly and then I think I've said enough, is what I like to think of as catness. So remember I told you about Milburn, and the idea is he didn't care about the cats. He had 2 subfigures that became figurative letters in Nature, but he cared about how to describe the evolution. So to me, I just think of it as a catness thing. Can I evolve the system into and out of a cat state? So in the experiments, as a way of characterizing the decoherence, we drive it to a cat, keep driving back in and out of cat state, and we can do that hundreds of times. But it gives us a window on the level of decoherence. And these things, once you ionize it, your open system dynamics is negligible. So nuclear physics is really good. I mentioned too, I don't know if people saw the recent breakthrough of thorium clocks at all. So the idea is that we use atomic clocks, but we could be moving towards nuclear clocks soon. And nuclei have a lot of advantages. And so now that I'm playing with nuclear instead of atomic physics, I'm discovering, I'm really seeing how amazing it is to work with nuclei, because you really do get nice Hamiltonian dynamics. End of transmission.
Cool, thank you. So I didn't understand what you meant at the end. What's nice Hamiltonian dynamics?
So you write down, you describe your system, and then you say it evolves according to a Hamiltonian, and that leads to unitary evolution. And then you wake up and realize, oh my goodness, it's not really Hamiltonian. Things are not unitary.
So just robust to noise, you're saying? Relatively robust.
Yeah, immune. I would say immune. So you say, I'll write down a Hamiltonian description, and I don't care about open system. I don't care about error correction. I don't care about anything. And I could even put my control in, and so everything is Hamiltonian.
But this is with a single system doing its own shit, not
Yes.
like if you try and couple them and
So
entangle them, then you make it messy.
yeah, the more degrees of freedom, and the larger the scale, the worse things get.
And if you're trying to control it, then there's some environment that is interfering,
Yeah.
and then I think.
But you're right, yeah. So like a nucleus has size, scale of femtometer. So the damage that you get to the nucleus would be the femtometer scale. But you couple two nuclei together on nanometer scale, and then nanometer and subnanometer stuff comes into play. You know, and then the bigger you get to condensed matter systems, and then it's a total mess. So yeah, it's nice. I just want a nucleus.
Anyone has a question? You have a question? Yeah.
I'm not sure I understood. What was the point you were trying to make when you mentioned super selection?
What was the point I was trying to make when I mentioned superconducting?
Super selection.
Oh, okay, so let's go through it again. So you know selection rules in atomic physics, right? And then there's like forbidden transitions, which aren't totally forbidden. You know, like a quadrupole transition is a lot slower. Okay, so the super selection rule is you say a transition is forbidden, not just negligible, but absolutely forbidden. So then, okay, in particle physics, something I'm exposed at a lot at CERN now in discussions, neutrino oscillation. You know about, yeah, so neutrino oscillation, you say you have three flavors. You get, like there's, electron, muon, tauon, there's the corresponding three types of neutrinos. But when they look for neutrino oscillation, the neutrino can be in a superposition of those. Okay, so now you say something like, can I imagine a lepton that's a superposition of being an electron, a muon, and a tauon? Is that allowed? Well, of course it should be. There's nothing in quantum mechanics, nothing in the standard model that forbids it, so it should be allowed. It should be allowed to have neutrinos in superposition, and we know this, and so experiments on neutrino detection focus on that. But then you go to somebody and say, what if I have a superposition of a proton and an antiproton? Or a superposition of electron and positron? And the tendency, and so it's not, it's documented, that people would say that can't be allowed. Why can't it be allowed? The thinking wasn't clear, but you go back to the Wick-Weitman-Wigner theory, you read through the Aharonov-Sasuke, and you see that they are allowed. But when they said they're not, that was known as super selection. You say, that transition is forbidden, there's no justification in quantum mechanics for forbidding it. It became part of the paradigm that particle physicists used. The solution to it is quantum resource theory stuff. Quantum resource theory, I can track it back and show you the evolution from those kinds of problems, but then quantum resource theory grew quickly and people kind of forgot the origins of the problem. So these are the origins of early thinkers on quantum resource theory that were then dropped later. So I'm kind of giving you the historical concept. Okay, so in the end, a super selection rule comes because you don't have the resource you need to be able to affect a transition. And then in quantum resource theory, it separates free from non-free resources and quantifies, to some extent, the non-free resource. Does that help?
I'd be keen to hear about that. Like, so Mighty works on resource theories.
That's why she's asking.
I'd like to hear more about that as well. But
In high energy, I always heard
So I can't make what you're
in
saying.
high energy, I heard always the rule was you can't put superpositions
Who told you that?
Like,
Yeah, there you go. Yeah, that's the point. They'll tell you things. You can't have this. I can't have it. Because your imagination's not there. Okay, but if you take supersymmetry, in supersymmetry, you write the supersymmetric creation operator. It's, in a sense, a superposition of creating a boson and a fermion. So maybe supersymmetry is wrong, but I can have it. It's only wrong in the sense it's not empirically established. It's still a theoretical possibility. But yeah, they'll say that all the time. And that's what I said. I'm at CERN these days. So I sit around at lunch or dinner, talk to somebody, and I ask them these questions. So I'm checking.
What's the resource that stops proton, antiproton?
You need the resource of a reference frame. So you say, like, it's kind of a bootstrapping problem. In fact, I'll tell you, it's an interesting story that the question of the coherent state being a superposition of number. But if you go through your theory of the laser from the, what's his name? Hawkins' theory of the laser. There were two different laser theories, but Hawkins' theory of the laser is population dynamic. Your laser can be fully described by some mixture of photon numbers in a cavity in your detector. You never need a superposition of number states to describe laser operation. People like Klaus Molmer have written a lot about this. So why do we want to use a coherent state? Why did Glauber introduce coherence? And why did Mandel and others not use it? And the answer is, you take a laser beam and then you split it. Do something to the beam, like put it through a refractive index, and the other one is the reference. Then you remix it. So if you always keep your reference frame in account, you never need to have, you can write a super selection rule that says you can never have a superposition of number states, and you'll get all the right answers. But if you pretend the reference isn't there, and you say, how do I measure the phase, then you need it. So the references manifest as duplicating your system. And that's what was in the Aharonov and Susskind paper, is they're saying, that's why the entangled coherent state came out, saying, we have charge, but we have two systems, the charge in superposition, if you like, and the reference charge. So you double the degrees of freedom, and that was the origins of the quantum resource theory concept. If that makes sense.
Not fully,
Okay.
but it's fine. We can try one on one over that.
Well, I'll try
I've got
this.
a bit more than intuition.
Okay, so the proton, antiproton.
Yeah.
Okay, so if we want to be able to do a Hadamard between, so you say, I have and this stuff I'm thinking, just these days at CERN, one of the projects I decided to work on is I want to try to work on teleporting antimatter. So I'm thinking about exactly this problem. So you send your proton, and then you say, I want to make a superposition. Well, if a NOT operation flips you from proton to antiproton, and that's a CPT transformation in particle physics. Asterisk, this is it's an anti-unitary transformation. So we have to deal with anti-unitarity, but if you put that aside, a Hadamard would be half a CPT. Then you have a superposition. But then, are you allowed to do a half a CPT? And so what you want to do is take into account, how do I convert protons to antiprotons? The way you do it is you annihilate, get gamma rays. Annihilation of a pair becomes a turnaround in time. You could go through all that, and then you get you can get the reference frame for it. I have a paper on this, the quantum resource theory for CPT. Nobody ever cites. You could be the first. But we went through the whole thing of quantum resource theory for CPT.
Okay, good.
And then it just becomes doubling you double your degrees of freedom. Essentially, it's all in a Aharonov and Susskind, but just a hard to read work.
I'm donating questions. Does anyone have any questions? If not, we're already over time, actually. So let's thank Barry again.